So I wanted to do an interesting topic in this second to last lecture, and I didn't want to start something super new, so I'm going to give you kind of a different perspective on these kinds of differential equations that we've been studying. So x prime equals ax, where x consists of n unknown functions, functions of time, of t, so like n dynamical variables that all together describe the state of a system that you're interested in, and then A would be an n by n matrix of coefficients. So in all the examples we've looked at, we've done n equals 2, but we're now very familiar with this, at least when n equals 2. And many of the same ideas we've looked at apply to n bigger than 2. You would just have a lot more computational work to do to find all the eigenvalues and eigenvectors. And you would also have to worry about the much richer variety of phase diagrams, which would now be pictures in higher dimensions. Anyway, I want to go back and notice that this looks a lot like, oh, by the way, actually, before I officially start with this lecture, this is not from our textbook, but I'm going to give you guys some notes that I wrote about this material. So the lecture is just going to be a lecture version of those notes. So take your pick. You can, you can do both, or you can only read the notes, or if you prefer to see videos, this is basically just going to be a video version of the notes. All right, so now we officially begin. So notice that the 1-by-1 version, where this is a 1-by-1 matrix and this is a list of just one function here, looks like this. You remove these annotations. The 1-by-1 version looks like this. X prime equals ax, where a is a 1-by-1 matrix, meaning it's just a number, right? Usually we wouldn't use a capital letter, we would use a lowercase letter, but this is what it would look like. And this is actually one of the first differential equations we considered at the very beginning of the quarter, and we're very familiar with the solution. The general solution, so the first solution that comes to mind is probably e to the at, right? That's the main famous function whose derivative equals a times itself, right? Its derivative is a times itself. And then the general solution would be just stick a parameter in front that could be any real number there. So that's the 1-by-1 version of this thing. Now, how could you have discovered this solution to this system? How could you have discovered this without necessarily knowing about the exponential function? So one way is separation of variables, right? But let's pretend that you haven't even defined the exponential or the logarithm function, so when you separate variables, you find yourself with this, this integral dx over x on the left side, and you haven't defined exponential or logarithm, and you're just like, well, I don't know what this integral is. How might you still discover this solution? Well, one way is to go back and define that integral to be the logarithm, and then define exponential to be the inverse of the logarithm. So that would be one way to go. Another way to go, if you haven't defined exponentials or logarithms yet, is to search for power series solutions. So starting with this, search for solutions that equal their own Taylor series, things whose Taylor series converge to themselves. This is called analytic solutions. So guess, it's basically like guessing an infinite degree polynomial. So guess not x of t equals just c0, nor just c0 plus c1 t, nor just c0 plus c1 t plus c2 t squared, but forever as a series. So basically guess something like this, Cn t to the n. So make this guess. And you know, with these infinite series, you have to worry about convergence. Depending on the terms of the series, it might or might not converge. So what we're guessing is something that we hope converges, so that we have a real number. Every time you put in a t, you get a real number out. Okay, so again, in case you zoned out, I'm asking, how would you find the solution to this if you had not yet invented exponentials or logarithms? So you don't know that there's something called e to the at. And what I'm saying is you could guess a power series form for your solution. So plug in the guess now. So if you have a power series, then power series have these wonderful properties. When they converge, that derivatives just work really well. So if you want x prime, you can actually just, even though it's an infinite series, you can just take the derivative of each term. So the derivative of c0 is 0. The derivative of c1t is c1. The derivative of c2t squared is 2c2t, and so on. 3c3t squared, and so on. So the derivative, if I write it in this form, the derivative is n cn t to the n minus 1, right? And n comes down. And actually, I can say that the sum just starts at 1, since the 0 term of the sum is 0, since I'm multiplying by 0. So I could take the sum to start at 1 or at 0. The n equals 0 term is 0 anyway, it doesn't matter. So that's the derivative. I'm finding the derivative because I need to plug my guess into the differential equation. So what I have found here is the left side. So let me copy over the differential equation and then replace different parts by my guess. So on the left side, x prime, let me remove that and then put what I computed it to be this. And on the right side, I have ax. So let me put in my guess x. So instead of x, I'm putting in this guess here. And actually, I don't know if you're finding this summation notation helpful. Maybe it's better not to use it, and just to write things with dot dot dots. I don't know what you prefer. I'm used to summation notation, but this is like the first and only time we do this in this course, so maybe better to do this. So here's my left-hand side, x prime, and then my right-hand side is a, and then x. X is c0 plus c1t plus c2t squared, etc. So there I've plugged in my guess. And I want this to be true for all t, right? I want this to be true for all t. So to make that happen, the functions 1, t, t squared, etc., these are linearly independent functions. We've encountered that fact before and used it many times while using the method of undetermined coefficients. These are linearly independent functions. So to make this equality work, to make this equality work for all t, we must have the coefficients matching up. So let me write down the coefficients on the right side. Let me distribute this a. Remember, the a is just a number here, not a vector, not a matrix. The a is just a number here. And I'm just distributing the a, is all here. So I've got the coefficient c1 here in front of t to the 0, and ac0 in front of t to the 0 here. And then I've got 2c2 in front of t, and ac1 in front of t here. And then 3c3 in front of t squared, and then ac2 here. So you see I'm getting this demand on the coefficients in order to have a solution. 3c3 is ac2. And this is kind of telling me what the coefficients have to be in terms of earlier coefficients, right? Like the first one tells me what C1 must be if I knew C0. The next one tells me C2 if I knew C1. So let me just write them. Let me write them like this. C1 is AC0. I'm going to keep that the same. And then C2 is 1/2 AC1. And then C3 is 1/3 AC2, and so on. So do you see the pattern? What's C4 then? It's 1/4 AC3, right? So this is a recursion rule, which is telling us later coefficients in terms of earlier coefficients. If you just know C0, then that tells you C1, which tells you C2, which tells you C3, etc. So let's write everything in terms of C0. It seems like just knowing C0 lets you propagate forward and learn about all the coefficients. So C2 is 1/2 AC1, so that means 1/2 AC0. So that's 1/2 A squared C0. This is 1/3 AC2, so 1/3 A, and then 1/2 A squared C0. That's what C2 is. So I have 1/3 times 1/2, so 1/3 times 2, times A cubed times C0. And then can you see what's going to happen here? I'm going to get 1/4 times 1/3 times 1/2 times A to the 4th times C0. Can you see the general formula? Cn will be 1 over, and then in the denominator I'll have n times n minus 1 times n minus 2, etc., all the way down to 2. This is called n factorial. And a to the nth power, C0. So this is the requirement on my original guess in order to have it be a solution to the differential equation. So remember where we started. We start with this differential equation, and we pretend we have not yet invented exponentiation or logarithms, but let's pretend that we know enough about power series to know that they behave nicely when you differentiate them, and it works like this. Then, if we were to guess a power series solution, then what would the coefficients have to do, if there's anything they can do, to make the power series a solution to the differential equation? So we plugged the power series in, and we got this requirement on the coefficients. So if the coefficients are like this, where you can choose the 0th coefficient to be anything you want, if the coefficients are like this, then you will have a solution. So x of t, I don't know why I'm still using yellow here, x of t equals, let me write it with dot dot dot, so C0 plus, and then C1 is, it's kind of cut off there, A C0 and then C2 is 1/2 A squared C0, which my face is covering right now. And then this one is 1/3 factorial, let's write it like that, A cubed C0. I'm sorry, I dropped the t's. Why did I do that? This is the coefficient in front of t. Let me make the t's even a special color. They're kind of important. This is the coefficient in front of t squared. This is the coefficient in front of t cubed. And so on. So the nth term of the sum is 1/n factorial a to the n C0. And we can pull out an overall C0 here, right? So we can view this as 1 plus a t all times C0 plus 1/2 a squared t squared plus 1/3 factorial. So this 2 actually was 2 factorial. a cubed, t cubed, and so on. Actually, you could view it like this. Okay, I'm just writing the same thing, but I could write at all squared here, right? A squared t squared is at squared. Oops. At cubed here, and so on. And hopefully this is starting to look familiar to you. This is the famous power series for E, which we have now discovered without having known it before. If we did not know it before, this would be a way of discovering it. So we now call this e to the at. Or let me do something a little bit nicer. Let's say this with t equals 1 plugged in, this with t equals 1 plugged in, so 1 plus a plus 1 over 2 factorial a squared plus 1 over 3 factorial a cubed, etc., shall henceforth be called e to the a. So that is our definition of e to the a. Then, making that definition, we have C0 e to the ta, right, or at, whatever you want to write. And so we've got that solution. You see the parameter in front that you're allowed to choose freely when you're trying to describe the general solution. That arose as an overall factor that was allowed to be multiplied by the whole thing. So maybe this definition is a little bit weird, since the exponentiation notation already has a meaning. Like when you write something to a power, that already kind of has a meaning, right? It means that number to that power. So what's the number e then? Isn't e to the a already defined to be the magic number e taken to the power a? Well, what I'm saying is pretend that we didn't know about the magic number e. Then we can call this, how about I write it like this, maybe this is more natural. We can call this exp a, where exp is the name of a new function that we're inventing. Sorry, exp a, if you plug in t equals 1. So exp a will be 1 plus a plus 1 over 2 factorial a squared plus 1 over 3 factorial a cubed, etc. And then we also define the magic number e to just be the exponential function evaluated at 1. That's all it is. So actually, the magic is not really in this number so much as in this function. And this number just happens to be what happens when you evaluate this function at 1. Which you might want to do if you want to view this as exponentiation with some base. The base would be this magic number. So I would say this is where the magic is, the exponential function. And then e is only special because it's the base for the special exponentiation function. All right, so in our pursuit of a solution of x prime equals ax, we discover this function exp a, the exp function. And as a side effect, we also discover this magical number, which is the value of that function at 1. And when you make this definition, then exp a becomes something that you can write as e to the a. That's because of an algebraic property that exp so one thing you can do, so pretend you have not yet defined exponentiation. One thing you can do after you start to look at this power series is establish that exp of one number times another number is exp of a product is going to be exp of this one taken to this power. so then exp of a is exp of a times 1 is exp of 1 taken to the a power, and then exp of 1 is called e. Okay, anyway, I'm getting sidetracked here. The point is, starting from the differential equation, we find ourselves with the power series for what we would call e to the at. That's the main point. And the idea now is to take this simple thing that we did with a 1-by-1 matrix, basically just taking a to be a number, and then try to do it for a being an n-by-n matrix. And you can do it, and you do end up with this as your solution, except a is a matrix. So at is a matrix, and so e to the at is the exponential of a matrix. So if we just repeat this process, but for a matrix A, then we will have a very nice compact way to write down the solution to this kind of differential equation system. So let's think about that in the next video.